Alrighty. Good morning, everyone. So I'm Craig Vineyard from Sandia National Laboratories, and this is joint work with several colleagues, but in particular with Brad Imony, William Sfera, and Stephen Verzi. And kind of as Kaushik was talking about, with the need for fundamental theory underlying computational principles, this work is going to look at what we can do in spiking regimes. Now, as many of you know here, depending on the semantics, how it's phrased, artificial intelligence, deep networks, machine learning are incredibly popular topics right now. They're incredibly prominent. There's big programs that we just heard about. And just a month ago, Google's CEO made a comment in which he was comparing the importance, the significance of AI to be on scale in terms of being profound with electricity and fire. And that's an elite company. Those are strong claims that leads to a lot of hype, a lot of potential. And so the question becomes, can neural-inspired computing elements help deliver on this potential? Can they live up to the hype? Can they deliver? And as a lot of you know, some of you may have even helped do some of the underlying formal derivations. People have known for a while that neural networks can do universal function approximation. And in this sense, you can construct arbitrary functions where, in combining neurons in clever ways, you can represent complex, sophisticated functions. Now, there are some caveats, namely, you have to have a continuous function. It's an approximation, so there's trade-offs in how many neurons you use, how accurate your representation is, how smooth your encoding might be. And so, for example, shown here, just illustratively, we have a one-dimensional example and a two-dimensional example. And on the one-dimensional example, it's a little bit smoother. It's a cleaner curve, but then on the two-dimensional example, it's a little blockier. And it's kind of the fundamental theorem of calculus that the more of these approximations you use, the smaller the representations are, the smoother curves you can get. But for the work I'm talking about here, I don't want to just explore how can we use this clever trick of using universal function approximation with deep networks, but rather the key principle that I want to dig into is looking at how can we combine neurons in a clever way, and how can we use these compositions and interesting architectures and configurations to perform a desired computation. How can we use the dynamics of these interacting neurons to yield some function? And so as a basic neural module, a building block to work from, so say you have this fundamental leaky ingredient fire neuron, and say you have a block which consists of P neurons. And each of these neurons has parameterization, as we all know. They can all have a spiking threshold. They can have a leakage rate. I didn't show these in the graphic for cleanness of illustration purposes, but innately they're operating in a temporal regime. And so they're giving a temporal output rho, which over time indicates whether or not the neuron spikes or doesn't spike. In this paradigm, we're using a unary encoding, and so with that, the sooner you fire, the more significant, the more magnitude you're trying to convey. And operating in that regime has certain complexity limitations. For instance, you can require exponential time in some cases, but there's also scenarios where, looking at the space-time resource trade-off, that we can give you optimal parallel randomized performance. And so extending upon this basic neural module, when you can combine them in interesting ways, first of all, showing some canonical machine learning computation, or not machine learning, some canonical computations before working into machine learning algorithms in particular, taking inspiration from a classic algorithm called spaghetti sort, in which if you want to be able to compare different magnitudes of numbers, and the lengths of the numbers are cast as uncooked strands of spaghetti, then if you want to be able to compare these numbers in parallel, you have a lever that you lower until it hits the top spaghetti. This is the longest spaghetti strand. And so you didn't have to do a whole bunch of pairwise comparisons. You don't have to enumerate each and every value, but you can then quickly extract this is the largest value. And taking that sort of fundamental idea, that notion, we can cast this cleanly into a neural regime where, instead of having the magnitudes of uncooked spaghetti, we have the strength of an input value. And as shown across the top, say we have 10 values that we're trying to sort. We want to examine their properties. The magnitude of their inputs is proportional to the size of the input value. And the quicker that they are able to spike and drive a threshold to be reached, can enumerate which is specific properties. So for instance, shown in the chart, expand this in time. So we have 11 neurons. We have represented by the rows across n. The 1 through 11 is indicating just an index of the neurons. It's not the actual input value that they receive. Then shown across the rows are time steps. And so in the very first row, the first value to spike immediately reaches threshold, indicated by neuron 8, is the largest value, in this case, a value of 9. And so one other parameter that I forgot to mention in describing this basic setup is that you have a defined temporal window. So in this case, we have a temporal window of k of 10. And so we're going to look at 10 time steps and look at the temporal properties of these time steps. In the second time step, there was no next value, so nothing's fired, everything's silent. The third value, the next largest value fires, and so on. And looking at the spiking behaviors, the spiking properties, we can extract out what's the maximum value, what's the minimum value, what's the median value. And as shown here, in doing so, we can construct neural circuits which enable you to implement these properties. And they have different characteristics that, depending on your dynamics that you allow, if you allow negative values, then shown in the top left, if we want to be able to find the minimum, perhaps you load all of your initial neuron weights, their values as negative values, and we give every neuron a unit input. Then by driving the values upwards, we can find the minimum value very quickly, that the first neuron to fire is the minimum value. We then have a readout neuron, a winner take all, and we can then end the computation. We don't have to wait for every single neuron to fire because we only cared about the extrema. We only cared about the smallest value. But there's some complexity trade-offs in doing this. Part of this is dependent upon, do you have enough neurons to match every single input value, or do you have more input values than neurons? Would this be the case where our input set n is larger than our number of neurons p, in which case we might have to break this up into stages. We have to have prior winners, and then subsequently compare from the subsets. Let's break this up in a distributed manner. Or conversely, we can look at the maximum. And it's a very similar circuit where we want to be able to preemptively load the input magnitudes of all of the values, drive the first neuron to spike as the winner, cut off the computation, don't keep sorting all of the others. And the winner take all layer, the output layer, just reads out what are the values. Now, in doing so, we've been able to optimally prove that under certain scenarios that this can be optimally efficient in terms of a PRAM model. And shown on the bottom right, we have some simulations in which we explored what are the trade-offs in looking at your set of your numbers that you're comparing versus how many resources you're using. And so comparing it with a conventional approach, which you have to do all of your pairwise comparisons, as well as using the innately parallel neural approach. In these cases, there's a trade-off at threshold where spiking and the conventional approaches trade off which is more efficient. And this is somewhat due to the fact that the statistics of the problem, that for bounded k, shown, I apologize, it's a little bit small resolution, but having k equals 8, so 256 possible inputs, that eventually when you start having more and more numbers, so this is saying that my set of possible numbers ranges is between 0 and 255, but as I have increasingly many of these numbers, if I'm trying to sort, say, 10,000 numbers and the maximum size can be 255, you increase your likelihood that you're going to have a maximum value, and it becomes quite easy for the neural approach to trivially find that solution. Now, extending this, both max and min are just extrema cases, but if you want to be able to have a complete sort out of your set, you simply iterate on this process. So you find the max, find the next max, find the next max. You just keep iterating through this procedure until all of your neurons have spiked. You reset them so that way they don't continuously keep firing, they don't receive additional inputs. And this enables you to help find a sorted list of numbers. And it has computational advantages that it scales quite cleanly, whereas classical approaches, as you get more and more numbers, they blow up based upon the exponential numbers of comparisons you have to do. But those were all just motivational, canonical computations that you can do with spiking neurons. Additionally, we've been exploring what can you do in more classic machine learning regimes. And a lot of your traditional statistical machine learning approaches are based upon doing a similarity or a distance comparison amongst points. That you want to be able to make some relationship, you want to be able to decide how do different data points, data entries relate to one another. And you can do this very cleanly in a spiking neuromorphic manner, very similar to the notion of finding a max or a min, an extreme of value, by coming up with a spiking similarity. And so in this case, in a very similar setup, you have some set of learned of values that you want to compare against. So in this case, you have p different templates you want to compare against, and you're going to be able to do the comparison in parallel. So giving it some weights, so these are going to be linear multipliers upon your inputs. This might be doing something like defining a center on or a center off template that you want to be able to compare against, or a specific input feature, or whatever your particular domain is. But you can define those characteristics, compare them all in parallel, find whatever is the closest match within whatever desired temporal processing, and come up with the first to fire as your most similar unit. Now, building upon that fundamental notion, we're started exploring how can you use this for some classic machine learning algorithms. And so KNearest Neighbor, it's usually machine learning 101, the first algorithm people ever look at, the non-parametric method of classification in which you have a set of labeled points, and in order to determine the classification of an unknown point, you, as illustrated on the right, so say you have this unknown diamond, and you want to be able to decide, is it a blue triangle or a green rectangle? So you find the K-nearest neighbor. So K is going to be defined in some manner. It might be an odd number, say 7. You compute your 7 closest points. Then you vote upon what was the majority of the classes. Extending that into the spiking regime, using the similarity, spiking similarity circuit that I just described, that's the first process where, in this case, your learned neurons are each a data point. So you have one neuron corresponding to each and every data point. You want to perform a spiking similarity, identifying the first K spikes. And so you have a second module that's simply a counter. It just has a threshold of K. And I didn't show it here for cleanness of illustration, but the K winner layer can then turn off the similarity layer so you don't continually perform the next nearest points. And additionally, the K winner counter layer also primes the max layer. And so the max layer is identifying the classes, whereas not only do the similarities spike, but they're mapped to their known classification. And then simply once the K winner layer gives an input which is great enough to immediately exceed threshold, whichever of the classes, however many classes there may be, receives the larger input, it'll drive and give you the classification, allowing you to implement the spiking nearest neighbor, K-nearest neighbor algorithm. Now, extending upon this and building a more sophisticated algorithm, adaptive resonance theory is an algorithm which has been developed by Carpenter and Grossberg going back to the 60s, and it's a family of online learning algorithms in which resonance is the key defining characteristic that tells their algorithm how to learn. And in their family of algorithms, they've experimented with looking at different parameters, looking at using binarized weights, looking at real valued weights, looking at different representations, looking at combining multiple modules, looking at how can we combine 2 different modules in a supervised, semi-supervised paradigm. But fundamental to the family of algorithms, this resonance phase drives learning where inputs are compared against a learned template. You then decide, is it given a new given input? Is it sufficiently similar to what we've already learned? And sufficiently similar is defined by a vigilance parameter. And so you check whether or not any of the existing learned representations match vigilance. If they're sufficiently similar, then you can just update the existing templates. But if they're not, then it drives a disconnect and you decide to allocate a previously uncommitted template. You grow what your existing representation are. This sort of paradigm strives to address some of the challenges that have already been talked about this morning in terms of stability and plasticity, trying to address when do I add new templates, when do I sufficiently use what I have, how do I modify what I need. And taking that paradigm and building upon some of the concepts that I just described, you can also develop a spiking art module, a spiking adaptive resonance theory. And so just using the same sort of computational paradigm that I've been, the same little trick that I've been exploiting throughout all of these core algorithms. So first you use a spiking similarity. So you have a set of stored templates, and you want to be able to decide from these templates which one is it most closest to. And so you can do this comparison in parallel. In this case, you can then define, since we're talking about a temporal coding, and you need to decide how long do I allow this execution to go, I can set my vigilance parameter based upon how quickly do any of the neurons fire. And so if none of the neurons reach threshold, none of the similarities are close enough within vigilance, within this time window, then you can decide that I need to allocate a new template, a new neuron. Or if one does exist, you can then, as before, you can terminate the computation, no need to finish computing all of the existing similarities, and modify an existing algorithm, an existing template accordingly. Now to expand upon this growing library of functions that Sandy has been exploring, we wanted to be able to make these approaches more amenable to people who aren't necessarily experts, who don't have to know what the underlying characteristics of your neural circuit are. They may not know the exact parameterization. They may not know how to map these techniques to existing emerging hardware. And so we've been developing fugu as an interface and a collection of spiking algorithms. And so illustrated here, we have a growing list of spiking algorithms, which can then generate an equivalent neural circuit to execute that computation. And we're working on growing backends to connect these to existing neuromorphic hardware. Shown here is just a demonstrative set of 3, but we're expanding this. As a concrete example, we've been looking at particle image velocimetry cross-correlation. So this classic engineering application looks at cross-correlations between particle flows. And so you might use this in something like a wind tunnel. You have a bunch of particles, and you want to be able to observe how are they being perturbed over time. So you have a bunch of forces pushing your particles in different directions. You want to be able to examine different response characteristics, turbulence parameters, other characteristics. And if you're just using this for a scientific application program, you may not want to know how do I create a neural circuit to do this. So rather, the end user might just have to specify the temporal cross-correlation as a sliding scalar product. So they just have to specify F and G, shown in the bottom left. And so just giving that to the API, we can then pull out the cross-correlation function, which shown in the bottom middle. William Severas helped lead developing a spiking version of this. And then you can map that to your desired hardware backend. So far we've mapped this successfully to a Sandia-developed spiking temporal processing unit, as well as we've mapped it onto the IBM True North, and we're in the middle of working on mapping this to Spinnaker as well. And shown in the bottom right is an illustrative example of how this maps to IBM True North. And so in this particular case, the different neuromorphic backends have different connectivity constraints, they have different mappings, they have different weight precisions, all sorts of implementation details that the end user who just cares about implementing cross-correlation doesn't have to know. And so our Fugu library helps generate this for them, and then shown in the top right is a timestamp sample showing just how some randomly generated particles are moving over time. And so, in conclusion, there's a lot of bold and exciting claims around neuromorphic computing. And shown here, I've shown some initial work that we're still expanding upon. We're doing the formal complexity analysis to understand what are the space-times trade-offs, to be able to show what certain conditions do you have to have, how many inputs do you have to have, how many resources do you have, what's the computational cost of operating in a unary coding across time. And being able to tie this so that way we can get a fundamental understanding of, by using these techniques and then implementing them on the various neuromorphic hardware that already exists or that we're going to hear about the next couple of days, how can we make this for an advantageous implementation so that way we can help enable some of the autonomy that we're striving for. And we're just scratching the surface. That I believe that there's a lot of potential, and I'm looking forward to seeing a lot of the algorithmic developments, as a lot of the new architectures are going to be unveiled over the next few days. And then just to, in case anybody's interested, to help try and tackle some of these challenges, me and a couple colleagues, William Sver and Chris Carlson in particular, have a neuromorphic hardware and practice and use workshop at this year's IJCNN. And so it's trying to address some of these practical issues, trying to bring awareness to more of the community who's typically just looking at neural algorithms, but what are some of the constraints of I/O loading, representations, what sort of software infrastructure exists? And so if you have any interest, talk to me, William or Chris, or we have a call for papers. We'd love to have you present there as well. Thank you.
So if there are any questions, we have a couple more minutes that are available.
Just a short question regarding the models and the algorithms that you implement. Do you look at stochasticity? What happens, for example, if you have weights that are somewhat stochastic or the neurons are stochastic? Are the results more degrading in the linear fashion smoothly, or is it catastrophic at some point, for example?
Yeah, that's a great question. And so we admittedly haven't exhaustively explored that, but it's somewhat, the answer depends. So with that starts introducing questions of, do you have a population coding? So is it a singular point of failure? Or do you have multiple representations? And you can start aggregating votes, as well as, depending on how detrimental that noise is, how the stochastic perturbations drive one answer into another. Those are all great things that we're trying to explore, trying to quantify whether there's a resilience that you can guarantee with certain characteristics. And in doing so, the interesting question becomes, how much additional resource do you have to allocate? How does that impact your computational trade-off? Does the robustness come for free or at unusable cost? But we're working on it, but haven't gotten there yet.
Hi, Craig. I was just wondering, when you were discussing your art algorithm, like what was the concept when you had a new module that you had to allocate in order to learn something that didn't match?
Right.
What was the concept of allocation of storage that you used in the neuromorphic context?
Yeah, absolutely. So that's always a hard question with art, that you have to have a latent unused capacity. And so you have to have a certain amount of neurons that you haven't yet adjusted any of their weights for. And in the pure theoretical sense, it just assumes that you can grow infinitely. But in bounded practical senses, you then have to start looking at trade-offs of, well, I no longer have any uncommitted nodes. Do I just stop that I can't add any more? Do I delete an existing template? You have to have some sort of replacement policy. And so we've just been currently living in we have the latent capacity, let's keep adding.
Maybe one more quick
Okay.
question.
Yeah.
You mentioned several times as many neurons as the data points, data samples. I mean, one of the important elements of learning is generalization. So how the spiking neurons cope with generalization? You cannot afford to have as many neurons as the data
generalization
samples.
in that sense. Yeah, absolutely. That's a great question. And so we're not as mature in that assessment yet. We have started looking at that in terms of some of the canonical computations, like some of the sorts, some of the max stuff in which you break up a problem. And so you're right, you may compute in phases, have a winner from the first batch, and then it changes the complexity. So you have to start looking at resource usage over time. Some of the time costs don't scale as well in that sense, but it's a hard problem. Yeah.
Let's go ahead and thank Craig again.
Thank you.